Okay, good morning, everybody. Get your clickers ready. We'll do some clicking here in just a minute. We're going to review some homework, some items from homework 19. And I want to remind you that if you get stuck on a homework problem and you're kind of high and dry and you're kind of flailing maybe a little bit, what you can do if it's not during my office hours and you don't have any study partners nearby, post a new thread in discussions. And then, because in a class this size, there's going to be somebody in web courses that's that's going to read it within a few minutes, and hopefully they'll be able to give you some tips. And if not them, then I'll be looking at it and I'll be able to give you tips. So in other words, don't wait until the last minute, come to school. Like we had a student, Dr. B, can you go over problem, problem 15 or something? And I said I'm not ready for it now, but if that student had started a thread on it, then I would have prepared a little bit of lecture slides for that particular problem. But even if I didn't, if he had started a thread with it, he would have been able to get some good guidance from you guys. And I know a bunch of you have already done that a number of times. Also, when you start a new thread, I saw a thread, I don't know who it is, but they did not activate threaded replies, and they did not activate liking. And you should do that, especially if you're trying to get tips on homework and stuff, because if you don't have threaded replies and liking, you don't really know. It's easier to keep things organized and know what's good and what's not good in a thread, because sometimes threads can get really busy. All right. Exam 2 is on the books. Exam 3 is coming up a week from today. Exam procedures, same as last time. I'm going to activate, and it may already be activated now, homework or mini review 6 and mini review 7 due next Tuesday for you guys at 10:30 a.m. for the other sections at different times. And hopefully those will open up. Now they're not that bodacious, but they're going to be useful. Another study tool. Exam 3 is important, and I want everyone in here. Good, you're looking up. Even you guys in the back row. I want you to crush Exam 3. You can sneeze as you do it. But whatever else you do, I want you to crush it like a bug. And if you do, then we'll be able to ditch one of your 3 exam scores. We'll ditch the lowest one that you've got. So if you have exam 1 or exam 2 kind of stinky for whatever reason, but you crush exam 3, ding, we keep 3 and your other good grade, and we ditch your lowest grade. All right, so that's going to come up. So right now we just got 2 grades on the books, whether they're righteous or dangerous. But after exam 3 is on the books and graded, you'll have, we'll do the best 2 out of 3. All right? in regard to studying for exam 3, a note to you about actually, let me back up. Office hours tomorrow, room 158 in the Physical Sciences building, which if you've never been there before, you go to the Student Health Center and then you keep going past the Counseling Center and then you keep going to the bus stop, and when you get to the shuttle bus stop there, you know, kind of at the corner of Libra and the Counseling Center, then that's the Physical Sciences building. And I'm in room 158 from 11 a.m. until 1 p.m. tomorrow. If you want to study with anybody, it's best to study with me, if you can make it. And what we do in office hours, you just come. If you can make it for 30 minutes, great. If you can't, you can't. But you come, and if you have a question, you know, like something from homework 18 that's still bugging you, we'll go over it. And we'll just go around the room. Whoever comes, they each get a chance, and we review stuff. All right? Melissa.
Can we look at our exam too?
You can look at your exams as well. We'll still do that. That's always offered. Oh, by the way, I forgot. Some of you have asked for your Scantron PDF, and I haven't done that. I'm going to try to get it done this week. All right. Plus the blurb sheets. I don't think I put those up yet either. I got a lot of stuff to do. My life, it's so complicated. Not like you guys. You guys have a simple life, right? Everything's smooth and nice. Yeah, right. Anyways, so SI review with Maria, Monday next week, 9 a.m. to 10:30 a.m. So there's your 90-minute review. Classroom Building 2, room 206. So that's on the second floor. And I don't know if that's a regular classroom or what, but is it? All right, so that'll definitely. Plus, she had some. Does she have some this afternoon after class? No, she only has. What does she have Tuesday SI? It's Tuesday 3:30 to 4:20, something like that. 2? Yeah. All right. All right, so then you got Monday. So this is Monday. Any question? I feel like I'm forgetting something. Any questions about exam 3? I'm forgetting something. By the way, we're going to be doing Chapter 8 material, even though there's no Chapter 8 in the website yet. I'll be giving you a PDF of some Chapter 8 stuff. We'll be doing that on Thursday. And we'll continue that after Exam 2. All right, let's take a look at Homework 19. And I want to go over with you, we're going to do some clicking, so have your clicker ready. We're going to go over some oscillator energy questions. And there's something important about the oscillator that I want to emphasize, and we're going to do some document camera work. And I forgot my talking PDF, so it's just going to be static document cam, and I'll embed them into the YouTube. It'll be pretty good. So the last time we looked at the unique potential energy function for a simple harmonic oscillator. Go ahead and write down that vocabulary term, simple harmonic oscillator, SHO. So a simple harmonic oscillator is basically typified by a spring, a mass on a spring on a frictionless table. All right? And if you have a mass on a spring on a frictionless table and you start it going boing, it's going to keep going that way. It's going to keep oscillating if there's no friction. All right? So simple harmonic oscillator, no friction. It's kind of an idealization. But the properties of the potential energy function, here's a little diagram. We're going to be using this diagram here in our clicker questions, by the way. The potential energy as the force also depends on displacement away from the equilibrium, left or right. Now, in the potential energy, SPE, it's actually the square of the displacement. And for that reason, the potential energy function is symmetric to the left and to the right. Now, that's different from free fall at the surface of Earth. You know, our potential energy function was basically minus mgy. And that is not symmetric with respect to the middle of the free fall. You know, so if you're free falling from 500 meters, there's nothing symmetric about 250 meters. It's just more of the same. But if you stretch an oscillator out, you know, to 18 centimeters or something, then negative 18 centimeters is going to be the same dynamics, except opposite directions. So here's the formula for it. SPE equals 1/2 kx squared, as we mentioned last time. Now, we also, as always, we have the kinetic energy, and that's 1/2 mv squared. Now, we're going to calculate, we're going to take a calculation all the way through to a calculation with our clicker questions today. We're going to start with some multiple choice, and then our last clicker question of the first half of class is going to be a calculation. So, and we're going to calculate a speed from 1/2 mv squared. Now, you put both of those together, and you get a total mechanical energy that's also fairly simple. Here it is. The letters, flaming letters. Capital E, total mechanical energy, Mark, is 1/2 kx squared plus 1/2 mv squared. Everything's normal. All right. As opposed to minus mgy for, you know, if this was a free fall problem. Okay. So if we're talking oscillator, simple harmonic oscillator in the x direction, yeah, 1/2 kx squared. You know, so whatever k is and whatever m is, if you know the mass and the spring constant, you're always going to be able to calculate momentum, velocity, everything. You get everything. You completely map it out. You know, no matter if you want to go centimeter by centimeter or momentum state by momentum state or speed by speed, velocity by velocity. You can always tell. And if you know that you're on the x, you know, if you know you're moving and what phase of your oscillation you're at, you know whether you're moving left or right. So you can always figure out everything. As long as you know the total mechanical energy at one position, like max compression on the left, which in this case is 18 centimeters negative, and or max compression or max extension, that's 18 centimeters positive. Or let's say you know the total mechanical energy at x equals 0, the equilibrium. You know, if you know that, so you know, so you can, you know, if you care about max compression, yeah, you can get that. You figure out everything. But if you know, if you want to try some other point like 10 centimeters, and yes, we're going to calculate kinetic energy at 10 centimeters. Yeah, you could do that. You know, 10 centimeters is like halfway through your free fall. You know, if you're part of the way down from your release point in free fall, you have a little bit of potential and a little bit of kinetic energy. You got a mixture. And the same thing here at x equals positive 0.10 meters, you have some potential and you have some kinetic, and you can work with that if you know the total mechanical energy E. All right, so let's go to the clickers now, and let's try to do some thinking. And I want you to jot down the specs for this spring system, the simple harmonic oscillator. Here we go. Here's your first question. your spring system the specs are spring constant, 120 newtons per meter. So that means to pull it out by 1 meter, it's going to take 120 newtons. All right, so a little bit of oomph. Mass is 0.240, so that's about 240 grams. That's about half of a bottle of water, a little bit less. All right, and so we're just going to calculate some stuff here now. So those are the specs. Make sure, because we're going to use it for all the next 3 or 4 questions. All right. Question 1, you pull it out to 18 centimeters, 0.18 meters, and you hold it. So, and then we're going to release it in a second, but for right now, we're just holding it there. What's the kinetic energy if you're holding it? 0. That's right. So, could you calculate the potential energy at 0.18? Yeah, you have the formula for 1/2 kx squared. So go ahead and do that. Total energy is always whatever potential energy you have plus whatever kinetic energy you have. And if your kinetic energy is 0, then okay, that narrows it down a little bit. Or as they say in Scotland, you take the high road, I'll take the low road. I'll get potential energy before ye. Is that how it goes? Not exactly. Good. Yeah, and exam day, you can't kibitz with your neighbor, but today, yup, definitely. So just kind of coordinating, reason together. Let me see what you guys have got. All right, let me see what you guys. Oh boy, I'm going to have to. Well, I can see that I'm going to have to get up a little earlier on Thursday. You guys are doing really good on this. Okay, 20 seconds, starting right now. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Come on. 185. Okay, 184 it is. Raise your hand if you voted for 1.944. Sweet. All right. So there's, and all right, let's see if I can take it a step further. All right, so that's 0.18 meters. That's max extension. Okay, nice, very good. How about an intermediate position? 0.10 meters. Riddle me this. What's the total energy at x equals 0.10 meters? Same situation. Okay, you let it go now, and now it's moving, and you snap this photo. And what's the total energy at that instant, at that position? 30 seconds. Twenty seconds. Make a decision. Before I click it, 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. Come on, 185. Nope. You know what? I believe that you're going to have to start thinking better, because the 9 o'clock class, they crushed this one. And 42% of you chose C. That is the correct answer. Remember, once you get the total energy at any position, it's ditto marks all the way down, if it's free fall table. Or ditto marks all the way across from left to right, if it's a harmonic oscillator that you're working with. Okay, so remember, total energy, ditto marks. Get one, you got them all. All right, now that you've got it, let's get the spring potential energy at 0.10 meters. We got the total. Yeah. Velocity? We're going to figure out velocity in a minute. We're going step by step. We're going to get velocity at this point, but you don't need the velocity to figure out total energy or potential energy. Yeah, so potential energy, all you need to know is the position. I mean, if you have K, because it's 1/2 kx squared. All right? But we're heading, that's where we're heading. We're going to get a velocity here in a second. Desiree. Yeah, but the part of that's the total energy equation. For this, all we want to know is part of that equation, the SPE. Yeah, the other one, it's the sum, but remember the whole principle of conservation of energy. Once you know total mechanical energy E at some point, it's ditto marks everywhere else. We didn't use V for, 0. Because the previous problem, you were still holding it. Now we're at 0.10 and it's moving, but for the total mechanical energy, once you figure it out at max extension, that was question number 1, I think, then you got total mechanical energy at all the other points, including 0.10 meters. All right, so you don't need V. Now, we're going to get V here in a second. All right. All right, 20 seconds. $15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh my goodness. Come on, 184. There we go. Yeah, you guys got that one. You crushed it. Okay. And that, you know what? Now that I think about it, that's a pretty easy one, because 0.1 squared is 0.01. And 0.01 times 120 is 1.2. And 1.2 divided by 2, 1.2 times a half is 0.6. So that one you can actually do in your coconut. Now, riddle me this, my wonderful students. Kinetic energy time. No, 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 no. No, 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 no. I've got total energy. I've got potential energy. I've got kinetic energy. Who could ask for anything more? What is that? It looks like you took a piece of mango and dipped it in yogurt. What is it? It's frosting? Good gravy, this explains a lot. Who could ask for anything more? Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Da-da-da-da. Very good. It's just 1.94 minus 0.6, so 1.344. All right, now, my wonderful students, make a note of that. It's your kinetic energy, because now we're going to calculate a speed. Here we go. Hit the refresh key, because we're going to enter into a number. We're going to enter a number in. Hit refresh, and then here we go. Okay? Here's your task. Calculate the speed at 0.10 meters. And we'll go over this calculation in case you get tripped up. So try not to get tripped up. Oh boy, getting a headache. Doing good. Make sure to round off carefully though. Actually, this one has a really nice calculation you don't have to round off, if I recall correctly. La, da, da. No, 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 no. Doesn't that make you guys sick, eating cake frosting? See, they can't even hear. Doesn't it make you sick, eating cake frosting? Doesn't that make you sick? You're right. So you're going to be buzzing off the walls for the next hour and a half with all that sugar in you. Thirty seconds. Okay, 50 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Let me look at these answers. Uh-oh, I see somebody that messed up a decimal point. 3 people messed up a decimal point. 1 person rounded off wrong. No, 2 people rounded off wrong. And that looks about... Here's another person that rounded off wrong. 2 people. All right, so there's a little bit of mess here. All right, raise your hand if you typed in 3.3. Okay. Got it? All right, good. Yeah, 3.3 is the answer for that one. Now, we're going to go over that on the document cam. And as I mentioned, I have some other things about the oscillator system that I want to dip into on the document cam. I forgot to bring my talking PDF notebook and pen, so we'll just use regular pencil and paper, and I'll scan these into a PDF and then embed them into the YouTube, so it'll work pretty nice. Okay. Oh, let me switch to the document cam. Okay, so I'll PDF this and then you'll be able to see, for some reason this thing's, that's a little bit better. Okay, so I have a spring system, x equals 0 is equilibrium. And we started it out here, we'll call it x1, 0.18 meters. We figured out the total mechanical energy out there. Let me bring this down here a little bit. And then now what we're doing is, we'll call this x2, 0.10 meters. We're trying to figure that out. So the spring constant, 120 newtons per meter, And the mass is 0.240 kilograms. And so what we're going to do is figure out the speed. Now, the kinetic energy was 1.344 joules. And also, that's by conservation of energy for a simple harmonic oscillator system. We figured out 1.344 at this position. So I'll write down at x equals 0.10 meters. That's x2. All right? Now, that's also equal to 1/2 mv squared. Right? So 1/2 mv squared equals 1.344 joules. So that's good. So, and we got the mass, so we can figure out v squared. Then we square root that and we'll get v. All right, so here we go. Let's see, 0.5 times 0.240 kilograms times v squared equals 1.344. And hey, you guys, I'm going to change this from joules to kilogram meter squared per second squared. And that's the same as a joule in fundamental units. Everything's fine. Jordan, everything's copacetic. You know, kilogram meter squared per second squared, perfectly fine. But we want to cancel kilograms, and we can now do it left and right. All right? So let me bring this down. This is now 0.120 times v squared, and I've canceled kilograms, and that's equal to 1.344 meters squared per second squared. And hey, you guys, that's what we want for the square of a speed. You know, speed is meters squared per second. Square of that is meters squared per second squared. So this is looking righteous. Now all we got to do is divide both sides by 0.120. And if I recall, this comes up to a nice round, or a fairly nice number. So that's about 11 point something. 11.2, even. Anybody verify that? 11.2? Yeah, okay. So this is 11 point. Now that's v squared. So v is going to be the square root of that. Which is 3.3 meters per second. So there's your answer. And that's coming from an application of this formula right here. 1/2 kx squared plus 1/2 mv squared for a simple harmonic oscillator without friction. If you had friction in there, it'd be way trickier. You could have an energy equation, but you wouldn't have conservation of energy because friction dissipates energy in the form of heat, usually. And so you can't really, but if you idealize it to no friction, this is perfectly fine. Let me ask you a question. This last form that I've got there, right here, this last form, does anybody see kind of like an overcooked momentum? Like a momentum, but it's not really a perfect momentum. It's kind of, you know, it's momentum-ish, but it's not. What do you see? Look carefully at that formula. No, not your phone. Look at the formula. Come on. Think. Do you see anything momentum-ish? Anywhere in this? What's that? Go ahead. Go. P equals mv. We don't see that. Or do we? Is there anything P equals mv-ish in there? You know, like the cousin of P equals mv? Look carefully. What do you see? You don't see? See, Daniel, you were making a jest, but that's exactly the right thing to point out. What do you see? How about that? It's not an MV, but it's MV-ish. It's got an extra V. All right? Now, here's definition of momentum. P equals mv. Now this one's got a square in it. So let's go P squared. P squared equals m squared V squared. Okay, now this has got an extra factor of m in it. So let's divide P squared divided by m. And there, my wonderful students, is something very important for us. Because now I can go back to my initial equation here, my energy equation, and instead of mv squared, I could put in this stuff, P squared over m. So let's do that. And I'm going to write this in red. Okay, E equals, 1/2 kx squared plus, all right, I got a 1/2 and then P squared over m. All right, so let's make that a little bit nicer looking. E, total energy, 1/2 kx squared plus 1/2 times 1/m times P squared. All right? That, my wonderful students, is a very important equation for us. Now I'm going to work this a little bit further for you on the next page. But let me pause for questions. Good? Good? All right, let's keep going. .cam page number 2. All right, so here's the equation. And notice that this energy formula, each term has a 1/2 out in front. And you guys in calculus that have had calculus, when you see a 1/2 out in front and a second power in the rest of the equation, that should tell you something. That should put you on high alert. It's got a 1/2 out in front. It's got a physical factor, k, in front of the x squared. And it's got another physical factor, m, 1/m, in front of the p squared. Let's divide both sides by E. Over here on the left, we have a 1. 1/2e times k times x squared. 1/2e, 1/m times p squared. And let me make a note. Capital E this is what we calculated on our first slide, 1/2 k times x1 squared. So max extension quantity squared times k times 1/2 That actually tells you the total energy. Now I'm going to leave it as total energy here, but let me point this out to you. It's important. This E, total mechanical energy, encodes the size of the oscillation. X1 is the amplitude of the oscillation in the x coordinate. It's important. This, my wonderful students, is a formula for an ellipse. But not on XY graph paper, on X comma P phase space graph paper. Remember we did that a couple weeks ago? Phase space. A phase diagram. And you don't need to know anything else than the fact that it's an equation of a... And, you may recall this from high school geometry or trig class. On XY graph paper, an ellipse looks like this. X squared over A squared plus Y squared over B squared. You may remember that from back in the day. And that will correspond to an ellipse like this. Kind of a sideways ellipse, in which this is A, the horizontal width is 2A, this is B, the vertical dimension, not the same necessarily, all right, and for which the area is pi times A times B. And that becomes the formula for the area of a circle, pi equals r squared, if you have a circle. A circle is an ellipse with A and B the same size, perfectly symmetric, left to right, top to bottom, any other direction. All right, now, because this is an ellipse, I'm going to make an ellipse in phase space now. All right, so X on the horizontal, momentum on the vertical. All right, and I'm going to go out to X1 and minus X1. Let me go a little further. Try to make these symmetric. And I'm going to go up here. This is maximum momentum, maximum rightward momentum. Hey, you guys, where is the momentum maximum for the oscillator, spring mass system? Is the momentum maximum at maximum extension, maximum compression? I should have made this a clicker question. Or at equilibrium? In the middle or to the side, left or right? It's in the middle. And the middle is where it is. So, and that's x equals 0. So maximum momentum up here and minus P max down here. And let me just try to... Now your ellipse is going to be perfectly straight up and down at the left and right edge, perfectly flat top and bottom. So I was really doing a terrible job first hour, but this is much nicer. And on a computer, of course, you can do it really nicely. Okay. So there's my ellipse. One and only one energy, total mechanical energy associated with this. So go ahead and label that with capital E. Now I'm going to do another diagram for you on the third and last page of the document camera. So this is page 3. If you have, and you can maybe add this to the diagram you already have. So here's my first one. Ooh, that's a bad. It's kind of stinky. Okay, so there's capital E. I'll just label this one by capital E. And this is X. This is P. Now, if you start an oscillator a little bit further out, this is X1 here. I'll write that. This is X1. If you started a little further out here, X3, it's going to have a higher energy. So let me label this one E1, and let me do a similar ellipse, a lot bigger. You guys can kind of follow me on this. It's going to be parallel to the first one. So it's going to be about like this. And this is, we'll call this E3. Okay. Different energy states. And different phase portrait or phase map in phase space. An oscillating system. What's the first oscillating system that we studied in this class? Last Tuesday, I think. What? What was it? Raise your hand. What was the first one that we studied? Look at your notes. You're not looking at your notes. You're just looking at me. Don't look at me. Look at your notes. What's the first one that we studied? Spring? No. Uniform circular motion. And guess what? Uniform circular motion is an example of an orbit. And for us, a gravitational orbit, like the space station or the space shuttle or any other communication satellite. But guess what also orbits? Electrons orbit nuclei, not by the gravitational interaction, but through the electromagnetic interaction, which we'll start studying on Thursday. My wonderful students, let me ask you one more question, if it please the court. What are the units of area for a phase space diagram like this? It's not square meters because it's not XY graph paper. What are the units of area? No, it's not joules. That would be a force and a displacement. We've got an X and a P. So it's kilogram meter squared per second. What's that? We've talked about it. Remember? Yeah. Newton? No. Yeah, were you raising your hand? Okay. Angular momentum. And let me just add one more comment to page 3. The natural unit for measuring area on a phase diagram in a physical system, especially electrons, protons, neutrons, nuclei, is Planck's constant H, the one constant that rules them all. And what we're going to find is that the periodic table, all the patterns in the periodic table are linked to measuring these ellipses in multiples of Planck's constant and no other size. Only certain sizes are allowed, and the ellipse is allowed if it has a multiple of Planck's constant. If it has Planck's constant times 1, if it has Planck's constant times 1.030225 or something like that, no, it's not allowed. And only those orbits of electrons are going to be allowed. So only certain ellipses. And when we talk about periodic table after Thanksgiving, yeah, we're going to be talking about Planck's constant and these ellipses. Now we've almost got everything that we want in place. Let's go back to the regular display. Next thing we got to talk a little bit more about interference. See, what we're heading for is the periodic table all semester. And we had to study angular momentum. We had to study kinetic energy and potential energy so that we could get to this point. We had to study oscillation so we could get to this point. And we studied waves so that we could get to the periodic table. So, a couple more interesting effects. So, two waves interfere if they come from different sources. So, if you think of waves, think of them as being identified by the source. So somewhere there's going to be a source of waves. Now, if you're out in the ocean, it might be a storm off the coast of West Africa and another storm off the coast of Nova Scotia. And somewhere in the middle of the Atlantic, waves from each source are going to interact. All right? And they move independently away. So the waves over there in Nova Scotia, they don't know jack about the waves down there in Africa until they meet in the middle. And then when they interact, that's when you get your cool effects, your interference effects. So at certain points in the middle of the Atlantic, you're going to get two wave crests at exactly the same location and exactly the same time. So that's like a rogue wave. If it were by the shore, that would be a super big surf. Okay? A really nice, kind of like that place in Portugal, Saint Nazaire, where they have those enormous waves coming in out of the North Atlantic. Just gigantic waves. At another point, half a wavelength away, you might have two troughs. And there you've got an extra deep trough. So if you're at the top of the rogue wave and you look over the side of your boat, you're just gonna like looking off a cliff to the bottom of the trough, because it's going to be twice as deep below sea level as the wave was. So until those waves interact, they're going to be medium-sized waves. So the trough might go 3 feet below sea level and the crest 3 feet above sea level. But when they interact, they double the crest and they double the trough. Okay? When you have that, It's called constructive interference. That's a vocabulary term. And this is actually going to be important for us when we study the periodic table. Constructive interference. Now, there's such a thing as destructive interference, and that happens when you get a crest and a trough at a point in space at a point in time where the crest and the wave coincide, and you get flat water. You get no wave. That is known as destructive interference. So for just an instant of time, your two normal-looking waves add up to, at this location, flat water. All right? Now, I'm going to give you some kind of idealized diagrams of how this works. Now, these are, as I said, these are idealized. Real waves in the ocean are bumps. They're crests and troughs. Crests and troughs moving from point A to point B. This picture here is just two crests. Okay, so it's kind of idealized. Crest A is moving from Nova Scotia towards West Africa. Crest B is moving from the coast of West Africa towards Nova Scotia. Now, somewhere in the middle, and they both have velocities. The velocities are those black arrows up above there. Somewhere in the middle of the Atlantic, let me get my cursor over here. Come on, baby. Here we go. Somewhere in the middle of the Atlantic, right here, they add together. Rogue wave. Really big. Double the amplitude. Those two look about the same amplitude. All right? Now, in a real ocean waves, you've got crests followed by troughs. This was just two crests. And we can produce waves like this, but it's not easy to do. One single wave going out. Now, after they interact, you get that rogue wave there, and hopefully it doesn't destroy your ship. They just keep going. They just keep motating. The one from the coast of West Africa, B, it just keeps on going out towards Nova Scotia. The one that started in Nova Scotia, A, it just keeps motating down towards the coast of West Africa, Cape Verde Island somewhere. All right? They do not destroy each other. And this is one of the signs that what is transmitted by a wave is energy and momentum. The water doesn't disappear. The water changes its appearance. And by the way, I want to reinforce the two waves are in phase. Equal phases here, April, means crest to crest. So crest is, one phase of a wave. Trough is 180 degrees away. So if we had two troughs, that would be phase to, they would be in phase. Now, destructive interference is like this. Now, one phase we got here coming from Nova Scotia is a crest. And the phase that's coming from the coast of West Africa is 180 degrees difference. It's a trough. Okay? Difference is pi. So 0 and pi. All right? When they interact right here out in the middle of the Atlantic, at this point and at this time, flat water, 0 amplitude. And what we would say is that the two waves at that location, at that time, are out of phase, 180 degrees out of phase, or pi out of phase. The phase difference is equal to pi. Or you would say they're out of phase by 180 degrees. Or you would just say trough and crest. That says the same thing. Okay, so they're out of phase. Now, if this were real ocean waves and you were hovering overhead in a helicopter so you could see, like 100 meters of the ocean, 100 meters square, you'd be seeing bunches of big crests, deep troughs, and flat waters. And they'd be distributed. You'd see flat water, deep trough, flat water again, big crest. And in all directions. You'd see it in 2 dimensions. So it'd be kind of cool looking. And you know, if you're out there in the water, sometimes, you know, when you see this is if you're out in the water and raise your hand if you've ever been in this situation. You're out in the water and some really big boat comes by. And you know, the wake from a really big boat. Let me change mics. The wake from a really big boat can really, discombobulate you if you're in a small boat. So if you're out there in the ocean and there's regular ocean waves coming in from West Africa, and then some boat comes really close to you, you got 2 different, and they're not aligned, and you're going to be going way up and then way down, and then there's going to be flat water in between. So it's kind of crazy. So when you're doing these things, you know, this is a simplified picture, but in reality, you got to think in 2 dimensions at least. And one more point here, and I'll add this again. After these 2 interact, trough B interacts with crest A, they just keep on going. You know, that energy is moving from the coast of West Africa towards Nova Scotia, and then wave A from the coast from Nova Scotia on down to the coast of West Africa. All right, so that's an example of interference. Now, I'm going to show you another example of interference. And this is a police officer with a radar gun. And I know that you are all very nice young men and young ladies, and that you never disobey the speed laws. But I have a confession to make. They have nabbed me here in Florida 3 times. I know, it's shocking, isn't it? 37 in a 25. I have a lot to confess to. But they do it by beats. And so I'm going to show you how that works. Now, the cops use radar. And they have a fancy receiver to measure beats. And beats occur in this kind of idealized picture where you have 2 waves of slightly different frequency and slightly different wavelength. All right, so one might be a wavelength of 20 meters and another one might be a wavelength of 20.7 meters. All right, if you have that, then you're going to have beats. And what happens is they don't see these 2, they look like over here, this first black line on the left, it looks like they're in phase. And they might be. And because you get a big crest over here, constructive interference. But they're slightly out of step. And so here by the middle black bar, they're completely out of phase. So you get flat water down here. You get jack. And then again out here, okay, a little bit further along, they're in phase again. And so you get a big amplitude. Now, if these were ocean waves, this is what you'd get. If they were sound waves, what you'd hear is loud, oscillating with faint in here, destructive interference, and then loud again. And this is what it means to have beats. And on Thursday, I'll bring in some equipment, and you'll hear beats, audio beats, auditory beats. It sounds like almost like a buzz, okay, or something from a monster movie or something like that. All right, now this is my picture, much better than that last one. This one's kind of, I don't know who did that, but it's not very good. This one is precise. Okay, now we have a slightly different system here, but I'm going to make the frequencies a little bit different, so the wavelengths are different. The black and the red. All right. So equilibrium, sea level, right down the middle. And you can see the first bump over here on the left is they're pretty much in phase. So over on the left side of the diagram, we're going to get big amplitude. But now look over here. Here, I've got trough, and right in here, kind of towards the middle, black trough, red peak. All right, so that's going to be flat water in there. All right. And then over here, they're looking crest to crest over here on the far right. All right, now I'm going to, now I don't even think you can maybe draw it if you want. But this is really what you want to look at. Okay, here's the speed. All right, here are the frequencies. And I just set up these frequencies so that I could get it a nice combination. And here's the combination. This is what you would hear in blue. So try to sketch this out. High amplitude. All right, so this is loud over here. All right? The blue is the sum of the black and the red. So if you heard the black through your red ear, the red through the other ear, your brain would combine them into this blue curve. And over here, so this is what you'd hear. Over here it'd be loud. And remember, these things are moving to the right. So this is actually what you'd hear first. And so you'd hear a faint interval of time, and then a loud one. But before the faint one, this is actually what you'd hear the first. Because it's all moving off to the right. So this peak on the right side, you hear that, loud. Then you hear the faint. And then you hear the loud again. Now that happens periodically if you keep these at the same frequencies, the two sources. So remember, this is, the red is the coast of West Africa, the blue is Nova Scotia, right? Two different sources, slightly different frequencies, and you get beats. All right, now I made the amplitudes pretty close to the same size. All right, now how do you figure out the beat frequency? Because the beat's going to be like and you'll hear it on Thursday. It's going to be like a buzz, almost like a, kind of a rattle almost. All right, all you do is you subtract the big one, or you subtract the small one from the big one. In this case, F2 minus F1. And that works out to 12.8 hertz. Now, for those of you that know your audio systems, 106.7 hertz is a deep bass note, right? Does anybody verify me on that? Your audio, so you're all slackers on audio. I thought for sure some of you would know that. Oh my goodness. College students used to be into stereos and stuff. I guess things have changed. Anyways, the wavelengths are here, and I set it up so that the wavelengths would be nice to work with. 0.75 and 0.67 for the red. The beat wavelength works out to 12.8 hertz. That's a really deep bass. You wouldn't hear it. You might feel it in your bones. But your ears don't hear quite that deep. Now, if the speed, so this is kind of an artificial system. I set the speed of sound here to be 80 meters per second. In reality, the speed of sound is about 4 times bigger than that. But, for a nice, easy, we're not done yet. For a nice, easy 80 meters per second, 12.8 hertz corresponds to a beat wavelength of 6.25 meters. And that's what this is. There's the wavelength for the beats. electronically, the police officer listens, he shines a radar signal at your car. It bounces off the metal on the front of your, or the back of your car, and comes back to him at a slightly, if you're moving, it'll be a slightly higher or slightly lower frequency. If you're moving away from him, slightly lower frequency. If you're moving towards him, slightly higher frequency. And then he compares it to the factory setting, and he'll detect beats, because it'll come in at something high, a few hertz high or a few hertz low. He'll detect that. And my wonderful students, from that, he can figure out your speed across the ground. And if it's 37 and a 25, you're busted. Now, on Thursday, I'll show you the exact formula that the police officer uses. All right? And then we'll start Chapter 8, Electricity and Magnetism. Okay, no homework, just come to class on Thursday.